All right, let's get right into it. Today, we're going to take one of those big, kind of scary, multi-mark exam questions and just tear it apart piece by piece. By the time we're done, you'll see that even the trickiest problems are really just a few simple steps chained together. So here's what we're looking at: a ramp on the back of a horse box. It looks simple enough, doesn't it? Well, the physics tucked away in this thing is exactly what examiners love to use to separate the top grades. A question like this can seriously make a difference. We are tackling question 10 from an AQA GCSE Physics paper. It's an 8-mark beast split into two parts. But we're not just going to find the answer. Oh no. We are going to deconstruct the mark scheme itself so you know exactly what an examiner is looking for to give you every single one of those marks. Okay, so the question eases us in with a 2-mark concept check. It's asking, why is it easier to use the rope than to just grab the handle? Just think about that for a second. What's the real physical difference between those two actions? Let's unpack that first part, shall we? The answer all comes down to one of the most fundamental ideas in all of mechanics: leverage, and this idea of a turning effect. And here is the absolute key difference. The rope and the handle are both trying to make the ramp turn around a pivot point. That's the hinge down at the bottom. But the crucial thing is, the rope is way further from that pivot than the handle is. This brings us to a concept called a moment. Now, a moment is just the physics term for the turning effect of a force. And the cool thing is, to get the same amount of turn, if you make your distance bigger, the force you need gets smaller. So because the rope gives you a bigger distance, you need less force to get that ramp moving. Simple as that. So, how do you actually write this down for the examiner? To get your 2 marks, you need to hit 2 specific points. First, for 1 mark, you have to say the rope gives you a greater distance from the pivot. Got it? Then, for the 2nd mark, you connect that idea to the force, saying, so a smaller force is needed. That's it. 2 points, 2 marks. Easy peasy. All right, now for the main event, the 6-mark calculation. This is where you really need a solid game plan. It might look intimidating, but trust me, we're going to slice it up into 3 totally manageable steps. Now, have a look at this diagram. It's key. It shows the ramp being held perfectly horizontal, perfectly balanced. You can see the forces involved, the ramp's weight pulling down, and an upward force from a spring pulling up. And critically, it gives us that distance from the spring to the pivot, 0.15 meters. This is everything we need to get started. Okay, step 1. Our first job is to figure out just how much upward force that spring is providing. Since the ramp is balanced, the turning effects have to cancel each other out. The question tells us the clockwise moment from the weight is 924 Newton meters. Well, that means the anti-clockwise moment from the spring must also be 924 Newton meters. We all know the formula, right? Moment equals force times distance. But we need to find the force, so all we have to do is a little bit of rearranging. That gives us our tool for this first step. Force equals the moment divided by the distance. Now we just pop the numbers in. The moment is 924. The distance from the diagram is 0.15, and that gives us a force of 6,160 newtons. And just like that, step 1 is done and dusted. So we have our force, but the question is asking for the energy stored in the spring. And to figure that out, we first need to know how stiff the spring is. In physics, we call this the spring constant, and we use the letter K to represent it. And finding K is actually pretty straightforward. We use a formula that comes from Hooke's law. It just tells us that the stiffness K is the force you put on the spring divided by how much it stretches, or what we call its extension. So let's use the numbers we have. We take the force we just calculated, that's 6,160 newtons, and we divide it by the extension given in the question, which is 0.250 meters. That gives us a spring constant of 24,640 newtons per meter. Step 2, in the bag. We are on the home stretch now. This is the final step. We've got the force, we've got the extension, and now we've got the spring constant. We have everything we could possibly need to calculate the elastic potential energy stored up in that spring. And to finally get that energy value, we use the formula for elastic potential energy. It's a half times that spring constant K we just found, times the extension squared. You can see how each step just beautifully builds on the one before it. So let's do a super quick recap of our game plan before we get the final answer. We use the moment to find the force, we use that force to find the spring constant, and now we're about to use that spring constant to get the final energy. It's a perfect logical flow. Now for what is arguably the most important part of this whole thing. Let's see how every single part of our calculation maps directly onto the mark scheme. This is how you guarantee those 6 marks. And check this out. This slide lays it out perfectly. Look at this. You get 1 mark just for showing the calculation for the force, and a second mark for getting the right answer, 6160. Then the exact same thing happens for the spring constant. 1 mark for showing your work, and a 4th mark for the correct value. Your 5th mark comes from putting your numbers correctly into that final energy equation, and the 6th glorious final mark is for getting the correct final answer. There's a mark for every single step. But here's a little pro tip. The mark scheme often allows for more than one right way to do things, and in this case, there's actually a faster route to the final answer. If you're a fan of efficiency, you're going to like this. There's another equation for elastic potential energy. It's a half times the force times the extension. If you use this one, you can skip calculating the spring constant altogether. You just take the force from step 1, the 6160 newtons, multiply it by the extension, and then by a half. This calculation would also get you those final 2 marks.
And you know what? It doesn't matter which path you take, because you arrive at the exact same destination. The final correct answer is 770 joules. And that is how you absolutely nail a 6-mark calculation.
So what started as a simple lorry ramp turned into a whole exploration of levers, springs, and energy. It kind of makes you wonder, doesn't it? What other everyday machines are out there just hiding all this amazing, complex physics, waiting for us to figure them out?